Imagine volunteering your descendants, children not yet born, grandchildren who will never know your face for a sentence they never agreed to serve, inside a sealed metal world they cannot exit, accelerating through radiation-soaked darkness toward a star none of them will ever remember choosing. That is what a generation ship truly is. Not the luminous arc of science fiction, not a noble colony vessel drifting serenely between suns. A generation ship is a closed civilization locked inside a container, asked to function without interruption for longer than the Roman Empire endured, with nothing flowing in from the outside and no door leading back to Earth. The most ambitious sealed ecosystem ever constructed on this planet began collapsing within months and barely survived 2 years before requiring rescue from the outside world. A generation ship would need to sustain a comparable system not for 2 years, but for centuries. The engineering is not the most daunting element. Keeping humanity itself coherent across that duration is, and the real numbers, when you examine them honestly, are considerably worse than most people imagine. If you find yourself drawn to journeys that fundamentally alter how you see humanity's place in the cosmos, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue bringing you stories like this one. Now, settle in, get yourself comfortable, and let us begin. The nearest star to our sun is doing something quiet and devastating to your sense of scale. Not through malice, through distance alone. Proxima Centauri sits 4.25 light-years from Earth. That figure sounds almost manageable, 4 1/4 of something. But a light-year is not a modest unit. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.25, and you arrive at a number the human mind was not built to hold. Roughly 25 trillion miles of vacuum, of radiation, of cold, so absolute that the background temperature of interstellar space hovers only a few degrees above the threshold where molecular motion itself ceases entirely. NASA's Voyager 1, launched in 1977, remains the most distant human-made object ever to leave our solar system. It has been traveling for nearly 5 decades. Its speed is approximately 38,000 miles per hour, faster than any bullet, faster than any conventional aircraft by orders of magnitude. At that velocity, Voyager 1 would require more than 73,000 years to reach Proxima Centauri. Pause on that number. 73,000 years. When Voyager 1 launched, the internet did not exist. 73,000 years ago, anatomically modern humans had not yet made their way into Europe. Neanderthals still moved across that continent, living and dying in a world that would not recognize anything we call civilization. The entire recorded span of human history, every empire built and toppled, every cathedral raised, every revolution ignited, every satellite launched, fits inside the last 5,000 years. Voyager would need to fly for 14 times that entire span simply to reach our closest stellar neighbor. And Proxima Centauri is not even a particularly interesting destination, it is merely the nearest one. This is the wall that generation ships were conceived to scale, not a wall of political will or financial resources, a wall of time. Human beings live, on average, somewhere between 70 and 80 years. Even the most optimistic projections for extending human lifespan do not push that ceiling meaningfully past 150. Interstellar distances, on the other hand, demand travel times measured in centuries or millennia under any propulsion system that respects the known laws of physics. The gap between a human lifespan and an interstellar voyage is not an engineering inconvenience. It is a categorical mismatch. No single crew can outlast the journey, not because the ship would break down, because the people would die of old age long before the destination appeared on any instrument. Faster travel would dissolve this problem, but faster travel refuses to cooperate with physics. To reach Proxima Centauri within a single human lifetime, a spacecraft would need to move at a meaningful fraction of the speed of light. At 10% of light speed, roughly 67 million miles per hour, the transit time falls to approximately 42 years. That fits inside a human life. But the energy required to accelerate even a modest crewed vessel to that velocity exceeds the combined destructive output of every nuclear weapon ever built, multiplied many times over. And that calculation covers only acceleration. Deceleration at the destination demands the same energy investment again. The fuel problem alone is catastrophic. Conventional chemical rockets cannot bridge this gap regardless of how much propellant they carry, because the mass of the fuel demands additional fuel to move it, which demands more fuel to move that fuel, a spiral of diminishing return that collapses into absurdity well before reaching interstellar velocities. Scale this for human P. Imagine volunteering your descendants, children not yet born, grandchildren who will never know your face for a sentence they never agreed to serve. Inside a sealed metal world, they cannot exit, accelerating through radiation-soaked darkness toward a star none of them will ever remember choosing. That is what a generation ship truly is. Not the luminous arc of science fiction, not a noble colony vessel drifting serenely between suns. A generation ship is a closed civilization, locked inside a container, asked to function without interruption for longer than the Roman Empire endured, with nothing flowing in from the outside and no door leading back to Earth. The most ambitious sealed ecosystem ever constructed on this planet began collapsing within months and barely survived 2 years before requiring rescue from the outside world. A generation ship would need to sustain a comparable system, not for 2 years, but for centuries. The engineering is not the most daunting element. Keeping humanity itself coherent across that duration is, and the real numbers, when you examine them honestly, are considerably worse than most people imagine. If you find yourself drawn to journeys that fundamentally alter how you see humanity's place in the cosmos, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue bringing you stories like this one. Now, settle in, get yourself comfortable, and let us begin. Music. The nearest star to our sun is doing something quiet and devastating to your sense of scale. Not through malice, through distance alone. Proxima Centauri sits 4.25 light-years from Earth. That figure sounds almost manageable, 4.25 of something. But a light-year is not a modest unit. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.25, and you arrive at a number the human mind was not built to hold. Roughly 25 trillion miles of vacuum, of radiation, kind of cold, so absolute that the background temperature of interstellar space hovers only a few degrees above the threshold where molecular motion itself ceases entirely. NASA's Voyager 1, launched in 1977, remains the most distant human-made object ever to leave our solar system. It has been traveling for nearly 5 decades. Its speed is approximately 38,000 miles per hour, faster than any bullet, faster than any conventional aircraft by orders of magnitude. At that velocity, Voyager 1 would require more than 73,000 years to reach Proxima Centauri. Pause on that number. 73,000 years. When Voyager 1 launched, the internet did not exist. 73,000 years ago, anatomically modern humans had not yet made their way into Europe. Neanderthals still moved across that continent, living and dying in a world that would not recognize anything we call civilization. The entire recorded span of human history, every empire built and toppled, every cathedral razed, every revolution ignited, every satellite launched fits inside the last 5,000 years. Voyager would need to fly for 14 times that entire span, simply to reach our closest stellar neighbor. And Proxima Centauri is not even a particularly interesting destination, it is merely the nearest one. This is the wall that generation ships were conceived to scale. Not a wall of political will or financial resources, a wall of time. Human beings live, on average, somewhere between 70 and 80 years. Even the most optimistic projections for extending human lifespan do not push that ceiling meaningfully past 150. Interstellar distances, on the other hand, demand travel times measured in centuries or millennia under any propulsion system that respects the known laws of physics. The gap between a human lifespan and an interstellar voyage is not an engineering inconvenience. It is a categorical mismatch. No single crew can outlast the journey, not because the ship would break down, because the people would die of old age long before the destination appeared on any instrument. Faster travel would dissolve this problem, but faster travel refuses to cooperate with physics. To reach Proxima Centauri within a single human lifetime, a spacecraft would need to move at a meaningful fraction of the speed of light. At 10% of light speed, roughly 67 million miles per hour, the transit time falls to approximately 42 years. That fits inside a human life, but the energy required to accelerate even a modest crewed vessel to that velocity exceeds the combined destructive output of every nuclear weapon ever built, multiplied many times over. And that calculation covers only acceleration. Deceleration at the destination demands the same energy investment again. The fuel problem alone is catastrophic. Conventional chemical rockets cannot bridge this gap regardless of how much propellant they carry, because the mass of the fuel demands additional fuel to move it, which demands more fuel to move that fuel, a spiral of diminishing return that collapses into absurdity well before reaching interstellar velocities. Scale this for human passengers, and the numbers do not merely become difficult, they become fantastical. The physics works for postage stamp-sized probes. It does not work for people. This narrows the options for moving human beings to another star down to 3. The first is cryogenic sleep. Freeze the crew, revive them at the destination. The problem is that reliable, reversible human cryopreservation does not exist in any demonstrated form. No human being has ever been frozen solid and successfully returned to life. Certain preservation techniques show limited promise for individual organs in laboratory settings, but scaling this to an entire living body and sustaining that state for decades or centuries without cellular damage remains firmly speculative. The second option is relativistic travel, pushing a vessel fast enough that time dilation becomes a meaningful factor. A crew moving at 90% of light speed would experience the journey to Proxima Centauri in under 2 years of subjective time. But achieving 90% of light speed resurrects the energy problem, amplified now by relativistic mass increase. The closer any object approaches the speed of light, the more energy each additional increment demands, climbing toward infinity as the limit approaches. Relativistic travel is not forbidden by physics, it is forbidden by energy budgets, so extreme they have no practical path to realization. The third option is the one that sounds most reasonable, precisely because it demands no new physics and no speculative technology. Instead of compressing the journey, you accept its length and design around it. You build a vessel large enough to sustain a human population indefinitely. The crew lives, works, reproduces, raises children, grows old, and dies aboard. Their children do the same. Their grandchildren after that, generation after generation, living and dying in transit, until descendants of the original crew arrive perhaps centuries later at a star their ancestors chose and none of them have ever seen. This is the generation ship. On the surface, the logic is almost beautiful. You do not need to violate physical law. You do not need to invent suspended animation. You do not need to produce energy equivalent to a stellar output. You simply need a vessel capable of sustaining life for a very long time, and people willing to begin a journey knowing they will not live to complete it. The problem of distance becomes a problem of patience. The problem of velocity becomes a problem of sustainability. Rather than fighting time, you surrender to it. You let time do the work while the ship crosses the void at whatever speed current or near-future propulsion can achieve. At 1% of light speed, roughly 6.7 million miles per hour, the transit to Proxima Centauri would take approximately 425 years. At 25 years per generation, that is around 17 human generations, long but not incomprehensible. Civilizations have outlasted that span. Religious traditions have endured far longer. Family lineages have persisted for centuries. Surely a well-provisioned, well-designed vessel could hold together across 17 generations. The ancient Egyptians sustained a coherent civilization for more than 3,000 years. The Catholic Church has operated as a continuous institution for nearly 2 millennia. If human organizations can persist for centuries on an open planet with all its disruptions and conflicts and catastrophes, why not aboard a carefully controlled ship? This reasoning has a powerful gravitational pull. It is the reason generation ships have returned again and again to scientific literature, futurist thinking, and serious engineering proposals for over a century. The concept appeared in recognizable form in Robert Goddard's private notes as early as 1918, was explored in fiction by Don Wilcox in 1940, and received rigorous technical treatment from researchers at the British Interplanetary Society during the 1980s and 1990s. The idea persists because it seems to do the impossible. It converts the most daunting problem in space exploration into a question of engineering scale. Build the ship large enough, stock it thoroughly enough, populate it wisely enough, and the stars become reachable. But the seduction conceals a trap. The moment you accept the generation ship as a concept, you have not simplified the problem. You have traded one impossible challenge for a different impossible challenge that merely appears more tractable from a distance. Consider what a generation ship actually demands. It is not a large spacecraft with additional sleeping quarters and expanded food storage. It is a fully closed, entirely self-sustaining world that must recycle every molecule of atmosphere, every drop of water, every gram of nutrition, every unit of biological and industrial waste without meaningful loss for centuries. Nothing can be imported after the moment of departure. Nothing can be restocked at any point during the voyage. The ship carries everything it will ever possess on the day it leaves Earth behind. Every breath drawn by the 15th generation must trace back to oxygen that was already aboard at launch. Every calorie consumed by the 10th generation must originate from agricultural systems established before their great-great-great-great-grandparents were born. Every drop of water must have cycled through purification systems that were themselves sealed inside the hull before any living passenger was old enough to understand what was happening. On Earth, ecological recycling is performed by a biosphere that required billions of years to evolve. It spans the entire surface of a planet and involves trillions of organisms interacting across thousands of interlocked chemical and biological cycles. When one component fluctuates, the system compensates elsewhere. Forests absorb surplus carbon dioxide. Oceans buffer thermal variation. The biosphere is not designed, it emerged. It is redundant, sprawling, and magnificently messy, and those qualities are precisely what give it its extraordinary resilience. A generation ship must replicate the essential functions of that planetary biosphere inside a sealed container. It must grow food, regenerate breathable atmosphere, purify water, decompose waste, and hold atmospheric chemistry within the narrow band compatible with human survival, all using artificial systems that have no planetary scale buffers to fall back on. If the oxygen generation system underperforms by 2% across a decade, the cumulative shortfall becomes a crisis. If a crop disease eliminates one staple food source, the nutritional architecture of the entire population must reorganize around what remains. If a microbial imbalance disrupts the waste processing cycle, toxic compounds begin accumulating in the air and water, with no external reservoir capable of absorbing them. The most ambitious attempt to construct a closed ecological system on Earth was Biosphere 2-3-14-acre glass enclosure built in the Arizona desert that sealed 8 crew members inside for 2 years, beginning in September 1991. The structure contained 7 distinct biome zones: a tropical rainforest, an artificial ocean, a savanna, a wetland, a desert, a coastal fog zone, and an agricultural area. It was designed to be completely self-sustaining, cycling all air, water, and food without external inputs. It began failing within months. Oxygen levels fell from the normal atmospheric concentration of 21% to approximately 14%, equivalent to the thin air found at roughly 14,000 feet of elevation. The cause was not a simple mechanical breakdown. It was a biological surprise. Microbes in the agricultural soil consumed oxygen at rates far exceeding initial projections, and the excess carbon dioxide they produced reacted chemically with exposed concrete in the structure, locking both carbon and oxygen into calcium carbonate compounds that could not be accessed by the living systems. The crew experienced chronic fatigue, cognitive slowing, and mounting difficulty with physical tasks. Crop yields fell below projections, leaving the team perpetually undernourished. 19 of 25 vertebrate species housed within the enclosure went extinct. Every pollinating insect died. Cockroaches and certain ant species thrived with no competition to constrain them. The system never found equilibrium. It lurched from one imbalance to the next, each correction revealing new instabilities that had been invisible until the previous crisis was resolved. Eventually, outside air had to be pumped into Biosphere 2 to prevent the oxygen deficit from crossing into life-threatening territory. That single intervention ended the experiment's status as a genuinely closed system. The most sophisticated sealed biosphere humanity has ever constructed could not sustain 8 people for 2 complete years without outside rescue. A generation ship would need to run a comparable system almost certainly more complex, serving a population hundreds of times larger, not for 2 years, but for 200, or 400, or 1,000. And unlike Biosphere 2, there would be no technicians on the other side of the glass. There would be no emergency air supply standing by. There would be no Earth within reach. There would be nothing beyond the hull but interstellar vacuum, stretching for trillions of miles in every direction, indifferent to whatever was happening inside. This is the first fracture in the elegant logic of the generation ship. The concept rests on an assumption that a closed ecological life support system can be made reliable enough to operate without external intervention for centuries. No such system has ever been demonstrated at any scale for any duration remotely approaching what the voyage would require. The longest continuously occupied habitat in space is the International Space Station, which has housed rotating crews since November 2000. But the ISS is not a closed system in any meaningful sense. It receives regular resupply missions carrying food, water, replacement components, and equipment upgrades. Its atmosphere is supplemented from pressurized tanks. Waste is removed and either incinerated in the atmosphere during cargo vehicle re-entry or returned to Earth for processing. The station's survival depends on an unbroken logistical lifeline to the surface. Sever that lifeline, and the station becomes uninhabitable within weeks. The ecological challenge, severe as it is, represents only the entrance to the labyrinth. Beyond it lies a cascade of compounding difficulties that most generation ship proposals acknowledge only briefly, if they acknowledge them at all. A generation ship is not a spacecraft with an unusually long mission duration. It is a civilization, and that distinction matters more than almost anything else in the entire analysis. A spacecraft has a crew. A civilization has a population. A crew is trained, selected, and unified around a shared technical objective. A population contains children who made no decision to participate, adolescents who push against authority, adults who hold conflicting views about governance, and individuals whose private ambitions do not align with collective requirements. A crew can be screened for psychological resilience and professional competence. A population cannot be screened across generations because you cannot predict or control who will be born, what they will value, or what they will choose to believe. The moment the generation ship accepts that it will carry multiple generations, it accepts that the majority of people aboard at any given moment will not have chosen to be there. The founding generation volunteers. Their children are born into the mission. Their grandchildren inherit it as circumstance rather than aspiration. By the 5th or 6th generation, no one aboard carries any personal memory of Earth, any direct connection to the original mission architects, or any experiential relationship with the destination. They were born on the ship. They will die on the ship. The mission is not their dream, it is their inheritance. And inheritances, as every generation in human history has demonstrated, are not always accepted with gratitude. This is where the ethical dimension of the generation ship separates itself from every moral question humanity has previously been asked to confront. Every proposal for interstellar colonization via generation ship implicitly assumes that one generation of human beings possesses the moral authority to permanently define the lives of every generation born aboard afterward. The founding generation makes the decision to launch. They understand the risks. They believe in the destination. Their consent is genuine and informed by lived experience. Their children's consent is not. their grandchildren's consent is not. And the consent of every subsequent generation is not merely uninformed, it is structurally impossible, because those people do not exist at the moment the decision is made. They cannot be consulted, they cannot negotiate, they cannot decline. On Earth, present generations routinely make decisions that constrain the future. Constitutions are drafted, infrastructure is laid down, environmental damage accumulates, national debts compound. But in every terrestrial case, future generations retain the capacity to revise what was imposed upon them. Constitutions can be amended, infrastructure can be demolished and rebuilt, debts can be restructured or abandoned. The irreversibility of any given decision is always partial, always bounded by the fundamental openness of the world and the accessibility of alternatives. A generation ship removes this capacity entirely. The descendants cannot reverse the decision to launch because the launch cannot be undone. They cannot select an alternative trajectory because no alternative exists. They cannot leave the community, pursue a different life, or withdraw from the mission's demands. Their reproductive choices may be constrained by population management requirements. Their professional paths may be dictated by the ship's labor needs. Their daily existence may be governed by resource allocation schedules written by people who died generations before them. They are, in the most literal and unambiguous sense, serving a sentence imposed by ancestors who believed the mission justified the imposition. No ethical tradition in the Western philosophical canon accommodates this degree of intergenerational binding without severe difficulty. Utilitarian frameworks might endorse the mission if the long-term benefit of establishing a human presence at another star outweighs the suffering borne by intermediate generations, but this calculation requires assigning a precise value to the welfare of people who do not yet exist, and weighing it against the concrete, measurable suffering of people who do. That comparison has never been satisfactorily resolved within utilitarian philosophy. Deontological ethics, which center on the inherent rights of individuals, would struggle to justify a project that permanently strips autonomy from people who have no opportunity to consent. Virtue ethics might frame the mission as an expression of courage and civilizational ambition, but would need to reckon with the fact that the courage belongs to the founding generation, while the sacrifice belongs to those who follow. The generation ship forces a confrontation with a question that terrestrial ethics has had the luxury of deferring. What are the living permitted to impose upon the unborn? On Earth, this question is buffered by the openness of the world. Future generations inherit environmental damage and accumulated debt, yes, but they also inherit accumulated knowledge, standing institutions, and the freedom to reshape both. Aboard a generation ship, future generations inherit a sealed world with fixed boundaries, fixed resources, and a fixed trajectory, constraint without freedom, obligation without choice, a mission without consent. Some theorists have proposed that the ethical problem can be softened by designing the ship to be comfortable enough that its inhabitants would not wish to leave, even if departure were possible. This argument has a troubling internal structure. It is, at its core, the argument that a cage becomes acceptable once it is furnished attractively enough that comfort is a substitute for autonomy, that material sufficiency replaces the freedom to determine one's own path. History does not support this substitution. Gilded cages generate their own species of resentment. The knowledge that one cannot leave transforms even luxury into confinement, because confinement is not defined by the quality of the surroundings. It is defined by the absence of an exit. Others have proposed that the mission itself supplies sufficient meaning to justify what is imposed, that participation in humanity's greatest voyage compensates for the loss of individual freedom. But meaning cannot be delivered from outside. It must arise from within. And the seventh generation, born into a world they did not select, traveling toward a destination they have never seen, may not experience the voyage as a grand adventure. They may experience it as a burden placed upon them by people who are long dead and beyond accountability. The dead cannot be argued with. They cannot be held responsible. They simply left, and left their decision behind them, sealed into the hull like everything else. Set aside the philosophical dimension for a moment. Set aside the social dynamics and the psychology and the governance. Focus on the physical container. The ship itself must be engineered to a standard that has no precedent in the entire history of human construction. Every structural component, every hull segment, every seal and pipe and valve and circuit board and pump must perform reliably for centuries, not with scheduled overhauls at a manufacturer's facility, not with replacement parts ordered from a global supply chain, with whatever the ship departed with, and whatever the crew can fabricate from the materials they carry. Modern naval vessels, among the most durable and sophisticated machines humanity builds, have operational lifespans of 30 to 50 years under conditions of continuous access to dry dock facilities, specialized maintenance teams, and global logistics networks. An aircraft carrier requires thousands of skilled workers at dedicated shipyards for its periodic overhauls. A generation ship would need to operate for 10 to 20 times that lifespan without ever visiting a maintenance facility. Its crew would need to manufacture replacement components from raw materials using fabrication equipment that itself degrades over time and must itself be maintained and eventually replaced. This creates a recursive maintenance problem of extraordinary depth. The machines that repair the ship also wear out. The machines that repair those machines also wear out. At some level of this cascade, you reach a layer of tooling that cannot be replicated aboard, either because the necessary raw materials were not loaded at departure, or because the fabrication equipment needed to produce it has itself failed beyond recovery. When that layer fails, the entire maintenance structure above it begins to deteriorate without a foundation. Materials degrade in ways that are individually invisible but collectively devastating across centuries. Metals fatigue under repeated stress cycles. Polymer seals harden and crack. Lubricants break down into their constituent compounds. Electronics corrode under the influence of humidity, temperature variation, and radiation. Micrometeorite impacts accumulate across the hull, each one creating a microscopic crater, a stress concentration, a fracture initiation site. None of these processes announces itself dramatically. Each one proceeds quietly, invisibly, across timescales that no individual generation can observe from beginning to end. A generation ship does not face a single catastrophic failure. It faces the slow, patient erosion of every physical system aboard, distributed across a duration long enough to outlast every human observer's ability to perceive the full trajectory of decline. And then there is the radiation. Beyond Earth's protective magnetosphere, space is saturated with ionizing radiation from two distinct sources. Solar particle events produce intense, periodic bursts of protons and heavier ions during solar flares and coronal mass ejections, energetic enough to be lethal in unshielded environments, but at least partially predictable and concentrated in time. The second source is far less forgiving. Galactic cosmic radiation is a constant, omnidirectional background of extraordinarily high-energy particles generated by supernovae and other violent astrophysical processes distributed across the galaxy. These particles travel at velocities approaching the speed of light. They carry kinetic energies that dwarf anything produced by solar activity. And they arrive without warning, without pattern, without pause. Approximately 1% of galactic cosmic ray particles are heavy atomic nuclei, iron, silicon, magnesium, traveling at relativistic speeds. These heavy ions present a shielding problem that has no satisfactory solution using currently available materials. When a high-energy iron nucleus strikes a conventional aluminum hull plate, it does not simply stop. It undergoes a process called nuclear spallation, shattering into a cascade of secondary particles, including neutrons, protons, lighter ions, and gamma radiation. This secondary shower can be biologically more damaging than the original particle because it is more diffuse and because neutrons in particular are extraordinarily difficult to shield against. The crew is exposed not merely to galactic cosmic rays, but to the secondary cascades those rays generate by interacting with the ship's own structure. Hydrogen-rich materials, polyethylene, water provide meaningfully better protection than metals because hydrogen nuclei absorb proton energy efficiently without generating as many secondaries. Several generation ship designs have proposed surrounding habitable sections with water tanks, serving simultaneously as shielding and as water storage. This approach reduces the threat from solar particle events substantially. But the highest energy galactic cosmic ray particles carry enough kinetic energy to penetrate meters of water or polyethylene and continue onward, leaving behind a trail of ionization damage through whatever biological tissue lies in their path. NASA estimates that astronauts on a Mars mission lasting approximately 3 years would accumulate a total radiation dose of roughly 1 sievert, a quantity associated with a 5% increase in lifetime cancer risk. A generation ship population, exposed to galactic cosmic radiation continuously across centuries of travel, would accumulate doses far exceeding this threshold unless shielding achieves a level of effectiveness that no current or near-future technology can provide. Magnetic shielding using powerful superconducting magnets to deflect incoming charged particles before they reach the hull has been proposed as an alternative to passive mass shielding. The concept carries genuine theoretical merit, but it faces practical obstacles that compound across centuries. The enormous power requirements for sustaining strong magnetic fields continuously, the difficulty of deflecting electrically neutral secondary particles such as neutrons, and the engineering challenge of maintaining superconducting magnet systems through the same centuries of material degradation that afflict every other system aboard. The biological consequences of long-duration galactic cosmic ray exposure extend beyond elevated cancer rates. Research conducted at NASA's Space Radiation Laboratory has demonstrated that exposure to simulated galactic cosmic ray environments produces persistent structural changes in the brains of animal subjects. Mice exposed to heavy ion radiation showed reduced neurogenesis in the hippocampus, impaired synaptic plasticity, and measurable deficits in learning and memory that persisted for months after exposure ended. These findings suggest that extended human exposure to galactic cosmic rays may gradually degrade the cognitive capacities, attention, memory, problem-solving that are most critical for operating and maintaining a complex vessel across centuries. Across multiple generations, radiation introduces a genetic dimension as well. Ionizing radiation damages DNA. Cellular repair mechanisms correct most damage, but some mutations escape correction and can be transmitted to offspring if they occur in reproductive cells. Over centuries of exposure at rates significantly higher than those experienced beneath Earth's magnetosphere, the ship's population would accumulate heritable genetic damage at an elevated background rate. This does not produce dramatic transformation. It produces a steady upward pressure on the incidence of genetic disease, developmental abnormality, and inherited cancer predisposition, a burden that grows incrementally with each generation, adding to the medical load that the ship's health systems must absorb. Those health systems must function without any external support whatsoever. A generation ship must be its own complete medical civilization. Trauma surgery for industrial and agricultural accidents, obstetric care for every birth across every generation, pediatric medicine for every childhood illness, dental care, ophthalmology, psychiatric treatment, infectious disease management, chronic disease management, geriatric care, end-of-life palliation, every specialty, every diagnostic capability, every surgical technique, every pharmaceutical compound must be available aboard, or the population goes without. Modern medicine depends on a global supply chain of staggering complexity. A single course of antibiotics requires pharmaceutical manufacturing facilities, quality control laboratories, distribution networks, and regulatory frameworks, an entire industrial and institutional architecture simply to deliver a small tablet of medication to a patient. A generation ship must replicate the essential functions of this entire system using only the equipment and raw materials loaded at departure. Pharmaceutical synthesis aboard such a vessel would require chemical processing equipment capable of producing hundreds of distinct active compounds from base materials, analytical instruments to verify the identity, purity, and potency of each preparation, sterile compounding facilities to convert synthesized compounds into tablets, liquids, injectables, and other delivery forms, and the pharmacological expertise to prescribe, dose, and monitor medications for a population whose physiology may be diverging from terrestrial baselines due to radiation exposure, altered gravity, and the unique biological environment of a sealed vessel. Surgical equipment presents its own replacement cascade. Cutting instruments dull, suture materials are consumed, imaging systems, whether ultrasound, X-ray, or magnetic resonance, contain components that degrade and require servicing. Anesthesia depends on specific chemical compounds that must be synthesized continuously. Sterilization consumes energy and chemical inputs with every procedure. Every surgical intervention depletes the ship's medical inventory by a finite increment, and that inventory can be replenished only through on-board manufacturing of steadily increasing complexity as simpler reserves are exhausted. The training pipeline for medical professionals must operate without interruption across every generation. Physicians require years of structured education and supervised clinical experience before they can practice independently. Aboard a generation ship, medical education must be delivered by the ship's existing practitioners who are simultaneously providing care to the entire population, teaching the next generation, and managing the deteriorating equipment they have inherited from the generation before. There is no teaching hospital, there are no visiting specialists, there are no medical journals arriving from an external research community. The ship's medical knowledge is a sealed reservoir, what was known at departure, supplemented only by what can be learned from the ship's own clinical experience. If a novel illness emerges aboard, whether from pathogen mutation, from an unexpected interaction between the ship's microbial ecosystem and its human population, or from an environmental contaminant that accumulated slowly over decades, the medical team must identify it, characterize it, and develop a response using only the diagnostic equipment and scientific expertise present in that generation. There is no center for disease control to contact. There is no global pharmaceutical industry to commission a new therapeutic. There is no external expertise of any kind. The ship's medical team is simultaneously the World Health Organization, the research university, the pharmaceutical manufacturer, and the clinical hospital for a sealed community of thousands, a community where an airborne pathogen can reach every inhabitant within hours. This is not the hardest part. The hardest part is what happens when you combine every one of these pressures: the ecological fragility, the radiation accumulation, the recursive maintenance cascade, the medical isolation, and ask a human society to manage all of them simultaneously, without external support, without the ability to import expertise or resources, and without any margin for the kind of institutional failure that every human civilization has eventually experienced. Because all of these pressures assume something that has never existed: a human population that remains cooperatively functional, technically proficient, socially coherent, and psychologically stable across centuries of sealed confinement, with no escape and no choice. The engineering can be designed, the ecology can be modeled, the genetics can be calculated. The people cannot be engineered at all. And that is where the generation ship concept encounters something it cannot design its way around. The ship has launched. Earth is gone, not obscured by cloud cover or diminished by distance the way a coastline recedes from a departing vessel, gone in a way that has no terrestrial equivalent. Within months of departure, the sun contracts to a bright point indistinguishable from thousands of surrounding stars. Within years, it becomes simply one faint light among countless faint lights. The ship is now the only world its passengers will ever inhabit. Everything they breathe, everything they drink, everything they consume must come from systems sealed inside the hull at the moment of departure. Nothing enters from outside. Nothing can be requested. The nearest possibility of rescue recedes behind them at whatever fraction of light speed the engines achieved. And with every passing hour, the energy cost of reversing course and returning grows more prohibitive than pressing forward. There is no ambiguous return threshold. Within the first decade, going back becomes practically impossible. The ship is committed, the people inside are committed, and from this moment forward, every atom of oxygen, every molecule of water, and every calorie of nutrition aboard is all there will ever be. This is where the engineering reality of a generation ship departs from every other machine humanity has ever constructed. A submarine can surface, a space station can be resupplied, an Antarctic research station can be evacuated. A generation ship operates under a constraint that has no precedent in the history of technology: total material closure, sustained across centuries. The technical framework for this is called a bioregenerative life support system. The concept is straightforward to describe and nightmarish to execute. Plants convert carbon dioxide into oxygen through photosynthesis, while simultaneously producing food. Human and organic waste is broken down by microbial systems and cycled back into soil nutrients and usable water. Water moves through filtration, condensation, and biological processes continuously. Atmospheric composition is monitored and adjusted to maintain the narrow band of gas concentrations compatible with sustained human life. Approximately 21% oxygen, less than 1% carbon dioxide, a balance of nitrogen, and carefully controlled humidity. On paper, the cycle is elegant. Carbon, water, and nitrogen each circulate through closed loops. Atmosphere to plants to humans to waste to microbes and back again. Nothing is destroyed in the chemical sense. Everything is transformed and returned. A well-designed bioregenerative system could theoretically operate indefinitely because it does not deplete its inputs. It merely rearranges them. In practice, the word theoretically does catastrophic work in that sentence. Real bioregenerative systems do not close perfectly. They leak not through dramatic structural breaches, but through thousands of microscopic inefficiencies that accumulate invisibly over time. Every airlock cycling loses a trace quantity of atmosphere. Every pass through a water purification system leaves behind a fraction of contaminants that gradually concentrate in the recycled supply. Every biological decomposition cycle generates trace chemical compounds that are not fully broken down, slowly accumulating in the soil, the water column, or the atmospheric mixture. These losses are individually unmeasurable across weeks or months. Across decades, they become detectable. Across centuries, they become existential. Consider oxygen alone. The human body at rest consumes roughly 350 liters of oxygen per day. During physical labor and a working population, maintaining a generation ship performs constant physical work. That figure climbs closer to 500 liters per person daily. A population of 1,000 people engaged in active ship maintenance consumes approximately 500,000 liters of oxygen every single day. Every liter of this must be produced by photosynthesis because there is no external atmosphere to draw from. The plants generating this oxygen require light, water, carbon dioxide, soil nutrients, and stable growing conditions maintained without interruption. If crop yields decline by even a few % due to a plant pathogen, a soil chemistry imbalance, or a malfunction in the lighting systems, the oxygen budget tightens immediately. The crew cannot simply breathe less. Their metabolic demand is fixed by biology. The gap must be closed by the system, and if the system cannot close it, atmospheric oxygen concentration begins falling. The Biosphere 2 experiment already demonstrated precisely what happens when this balance breaks down. Oxygen plummeted, carbon became chemically locked in concrete. The world's most sophisticated sealed ecosystem nearly killed its crew within 2 years. But the specific lesson for a generation ship is considerably worse than the headline failure suggests. Biosphere 2's atmospheric crisis was identified, analyzed, and partially understood because the team maintained continuous communication with scientists on the outside. They could consult atmospheric chemists and ecologists who were not sealed inside the enclosure. They could receive analytical instruments that had not been included in the original design, and ultimately, they could pump in outside air to prevent the crisis from crossing into lethal territory. A generation ship crew confronting an equivalent atmospheric anomaly would have none of these advantages. They would need to identify the problem using only the diagnostic equipment aboard. They would need to determine the cause using only the scientific expertise present in the current generation of the population. They would need to devise and implement a solution using only the materials and fabrication capabilities the ship carries. And they would need to accomplish all of this before the oxygen shortfall reached a level incompatible with consciousness. With no external consultation, with no emergency reserve, with no Earth, the Biosphere 2 failure was recoverable because it occurred on a planet. The same failure aboard a generation ship 3 centuries into its voyage would be recoverable only if the crew possessed the precise combination of knowledge, equipment, and materials required to address it. If any element of that combination was missing through knowledge erosion across generations, through equipment degradation, through material depletion, the failure would not be an experimental setback. It would be an extinction event contained within a metal hull, drifting through interstellar space. Water recycling presents its own compounding cascade. A closed water system must purify all fluid consumed by the crew, and all water used in agriculture, metabolic wastewater, agricultural runoff, atmospheric condensation, and industrial process water. Modern water recovery systems aboard the International Space Station now reclaim approximately 98% of water from urine and cabin humidity, a milestone NASA confirmed in 2023 and rightly celebrated as a remarkable engineering achievement. But for a generation ship receiving no resupply, that 2% loss per cycle is a slow death sentence across a sufficiently long timeline. Even at the celebrated 98% recovery rate, cumulative losses would significantly diminish total water reserves within decades of continuous operation without some mechanism to compensate. A generation ship would need water recovery rates approaching 99.9% or higher, sustained without degradation across centuries. The purification systems achieving this would themselves require maintenance, filter replacement, membrane regeneration, component repair. The chemicals or biological agents used in purification would need to be manufactured aboard from raw materials. The energy required for continuous water processing would represent a substantial fraction of the ship's total power budget. Any interruption in the water recycling chain from equipment failure, chemical contamination, or microbial interference would begin depleting the single most critical resource aboard within days. Food production cannot rely on stored supplies. Preserved provisions have finite shelf life even under ideal conditions. Freeze-dried meals lose nutritional completeness over years. Canned goods degrade over decades. No preservation technology exists that could maintain edible, nutritionally adequate food for centuries. The ship must grow virtually all of its nutrition from living agricultural systems operating without pause across the entire duration of the voyage. These farms face constraints that no terrestrial agriculture has ever encountered. There is no weather, no seasonal cycle, no wild pollinator population, no natural replenishment of soil nutrients. Every parameter must be artificially governed. Lighting tuned to photosynthetically optimal wavelengths. Temperature regulated for each crop variety. Nutrient solutions continuously adjusted based on real-time monitoring. Pollination performed mechanically or by managed insect colonies maintained specifically for that purpose. Pest control accomplished without chemical pesticides that would contaminate the closed water and atmospheric systems. Crop diversity is not optional. Human nutritional requirements span vitamins, minerals, essential amino acids and fatty acids that no single crop provides. The agricultural system must grow grains, legumes, vegetables, fruits, and some form of protein source fish in recirculating aquaculture systems, insects, or laboratory-cultured cellular protein. Each of these food systems carries different requirements for light intensity, water volume, temperature range, nutrient composition, and growing cycle duration. Managing this agricultural complexity in a sealed environment with zero tolerance for total crop failure represents a challenge that eclipses anything attempted in controlled environment agriculture on Earth. And crops fail on Earth, routinely, with consequences that farmers manage by switching varieties, importing seed stock, or leaving fields fallow. A generation ship cannot import anything. It cannot rest its agricultural area because the population needs to eat every day without exception. A pathogen that enters the wheat cultivation section will reach the rice section because the entire agricultural system exists within a single enclosed volume where air, water, and organisms circulate continuously. Geographic isolation, the primary mechanism by which terrestrial agriculture contains disease outbreaks, does not exist aboard a sealed vessel. Quarantine is a matter of degree, not of kind. Now, consider energy. Nuclear reactors are the only plausible primary power source for a generation ship. They offer the highest energy density and the longest operational lifespan of any known power technology. But even nuclear reactors have finite fuel supplies and components that degrade progressively under neutron bombardment. Reactor pressure vessels become brittle over decades of operation as fast neutrons displace atoms within the steel crystal lattice. Control rod mechanisms wear, coolant systems develop leaks, fuel assemblies deplete. Modern commercial nuclear power plants have operational lifespans of 40 to 60 years, achieved through continuous access to external maintenance facilities, fuel fabrication supply chains, and workforces drawn from national populations of millions with deep institutional expertise. A generation ship reactor would need to operate for 5 to 10 times that duration without an external fuel supply, without access to specialized maintenance facilities, and with a maintenance workforce drawn from a total population of perhaps 10,000 people, of whom only a small fraction will hold nuclear engineering expertise in any given generation. Breeder reactor designs which generate new fissile material from fertile isotopes, theoretically extending the fuel supply, introduce additional engineering complexity, additional failure modes, and additional radiological hazards. Their maintenance demands are greater, not lesser, than conventional reactor designs. The energy budget of a generation ship clarifies just how narrow the operational margins become when every system draws from a single finite power source. Agricultural lighting alone represents an enormous continuous drain. Plants require light intensities comparable to direct sunlight for optimal photosynthetic output, roughly 1,000 watts per square meter of growing area for the most demanding crop varieties. A population of 20,000 people fed through intensive closed agriculture might require hundreds of thousands of square meters of growing area, each demanding high-intensity illumination for 12 to 16 hours out of every 24. Agricultural lighting alone could consume hundreds of megawatts on a continuous basis. Atmospheric processing adds another major sustained load. Carbon dioxide scrubbers, oxygen concentrators, humidity regulators, thermal management systems, and the fans that circulate atmosphere through every pressurized section of the vessel run without pause. Water purification systems pump, filter, distill, and chemically treat every liter consumed and excreted by the population and every volume of agricultural and industrial process. Water continuously, without interruption. Waste processing systems decompose biological and industrial waste through combinations of microbial digestion, thermal treatment, and chemical transformation, each stage consuming power. Maintaining artificial gravity through rotation requires continuous energy input to overcome friction losses in the bearing assemblies, connecting, rotating, and non-rotating sections. Fabrication equipment, machine tools, additive manufacturing systems, smelting furnaces, chemical processing apparatus draws power intermittently but at high peak loads when operating. Medical equipment, navigation instruments, computing infrastructure, communication systems, and the thermal regulation that prevents the ship from freezing in the interstellar void all contribute to the continuous baseline demand. A conservative estimate for the total sustained power requirement of a generation ship supporting 20,000 people falls somewhere between 1 and several gigawatts, comparable to the output of a large terrestrial nuclear generating station. But a terrestrial generating station operates within a grid that includes backup capacity, fuel supply chains, and a maintenance workforce drawn from a national population. A generation ship must produce this power from onboard reactors with no external fuel supply, no backup grid, and a technical workforce that must be continuously trained and retrained from within a closed population across every generation of the voyage. If reactor output declines by even a modest percentage through fuel depletion, component degradation, or a gap in the maintenance schedule, the resulting power deficit must be allocated across all competing demands. Which system receives less? The agricultural lighting, the water purification, the atmospheric processing, the medical equipment. Every reduction in power to any one system produces downstream consequences that propagate through the ship's interconnected infrastructure. A 5% reduction in agricultural lighting reduces photosynthetic output and crop yields. Reduced yields mean less food and less oxygen production. Reduced oxygen production increases the burden on atmospheric processing systems. Increased atmospheric processing load demands more power from reactors already operating at reduced output. The deficit deepens, the spiral tightens, and every turn of that spiral consumes resources that cannot be replenished from outside. This is the architecture of cascading failure in a closed system. On Earth, cascading failures in complex infrastructure, electrical grid blackouts, industrial accidents, ecological collapses are eventually arrested by external intervention. Replacement equipment arrives from outside the affected system. Emergency personnel come from unaffected regions. Resources flow in from areas the cascade has not yet reached. The cascade is bounded by the fact that the world is large, and most of it remains functional. Aboard a generation ship, there is no external intervention. There are no unaffected regions. There is no larger world to draw from. The cascade either stops because the crew successfully arrests it, using only what they carry: the knowledge, the equipment, the materials present in that generation, or it continues until it reaches a system whose failure is incompatible with survival. The oxygen stops flowing, the water stops being purified, the food stops growing. Any one of these endpoints is fatal, and the margin separating a manageable partial failure from a fatal cascade may be narrower than any pre-launch analysis can reliably predict, because the failure modes that matter most are the ones that emerge from the interaction of systems over timescales too long for any single generation to observe from beginning to end. The engineering reality of a generation ship is not a single dramatic challenge to be heroically overcome. It is an accumulation of slow erosions, each individually manageable in the short term, each collectively lethal across the centuries involved. The ship does not explode. It does not collide with anything in a cinematic instant. It runs down slowly, imperceptibly, inevitably, like a mechanism, with no one to service it in a room, with no door to the outside. And everything described so far assumes something that has never been demonstrated. A crew that remains competent, motivated, organized, and unified across centuries of sealed confinement. A civilization that neither fractures nor forgets. A population that transmits the technical knowledge required to maintain these systems across generation after generation without distortion or loss. What happens when that assumption fails is where the generation ship concept encounters something it cannot engineer around. Because the machine can be drawn on paper, the civilization that must operate it cannot be drawn at all. Every challenge examined so far rests on a single assumption that has never existed anywhere in human experience. A population that remains perfectly cooperative, technically capable, socially stable, and psychologically resilient across centuries of sealed confinement with no external contact, no possibility of escape, and no choice about any of it. The engineering problems are severe. The ecological problems are potentially fatal. But both categories share a common feature. They can, in principle, be modeled, tested, and designed against using physics, chemistry, and biology. The human problems that a generation ship must solve cannot be approached with equivalent precision because they involve the one variable that no equation has ever reliably captured: how people behave when they are trapped. The population question arrives first because it constrains everything else. A generation ship cannot carry an arbitrary number of people. Every additional person requires more oxygen, more water, more food, more living space, more waste processing capacity, and more mass that must be accelerated to interstellar velocity. The energy cost of the voyage scales roughly with the total mass of the vessel. and the life support infrastructure each person requires makes human mass among the most expensive cargo imaginable. There is an overwhelming engineering incentive to minimize the population aboard. But genetics imposes a hard floor on how small that population can be. When a small group reproduces in isolation across many generations, two related processes erode genetic health simultaneously. Genetic drift randomly eliminates gene variants when too few carriers exist to reliably pass them forward. Over multiple generations, drift strips diversity from the population the way wind strips soil from an exposed hillside, slowly, invisibly, irreversibly. Inbreeding compounds the damage. In a small, closed population, individuals inevitably become genetically related within a few generations. Mating between relatives increases the probability that offspring inherit two copies of harmful recessive gene variants. The consequences accumulate with each generation: reduced fertility, elevated infant mortality, higher rates of congenital disease, weakened immune response. These are not theoretical predictions. They are documented outcomes observed in isolated human populations throughout recorded history. The Pitcairn Islanders, descended from 9 bounty mutineers and 18 Polynesian companions who settled the island in 1790, maintained a population of roughly 50 to 200 people across more than 2 centuries. They survived. But medical examinations revealed elevated rates of certain genetic conditions consistent with the founder effect and prolonged reproductive isolation. The inhabitants of Tristan da Cunha, the most remote permanently inhabited island on Earth, descended from 15 original settlers and subsequently showed elevated rates of asthma traceable to 3 specific founders who carried the genetic predisposition. Both populations survived because they were not truly sealed. Occasional immigration introduced fresh genetic material that partially offset the accumulating inbreeding effects. A generation ship has no immigration, 0. The founding population constitutes the entire genetic resource for the duration of the voyage. No new hereditary material enters the system until arrival at the destination, which may be centuries distant. This makes the genetic constraints far more severe than any terrestrial analogy adequately captures. Anthropologist John Moore estimated that a carefully structured founding population of approximately 160 people screened for genetic diversity, organized into age-balanced reproductive cohorts, and governed by explicit mating protocols designed to minimize inbreeding, could sustain adequate genetic diversity across a 200-year voyage. But Moore's figure rested on assumptions of optimal social compliance across every generation. Every individual follows prescribed reproductive arrangements without deviation. No catastrophic population losses occur from disease, accident, or conflict. The social engineering required to enforce reproductive pairing across centuries actually functions as designed. Anthropologist Cameron Smith challenged this optimistic baseline in research conducted as part of Project Hyperion. Smith's analysis incorporated realistic assumptions about demographic variability, the statistical probability of catastrophic mortality events, and the likelihood that some fraction of individuals in any generation will not reproduce due to infertility, personal choice, or premature death. His models indicated that a genetically viable founding population for a multi-generational interstellar voyage would need to fall somewhere between 14,000 and 44,000 people, with a recommended working figure of approximately 20,000 to 40,000. Not because the theoretical minimum is that high, because real populations experience shocks, and a population must be large enough to absorb those shocks without falling below the threshold where genetic viability collapses. Consider what a population of even 20,000 people, the lower boundary of Smith's recommended range, actually means for the ship. 20,000 people require living space, working space, recreational space, agricultural space, industrial space, medical facilities, educational infrastructure, and governance architecture. They generate waste at scale, consume resources continuously, and require social structures complex enough to manage disputes, allocate labor, enforce behavioral norms, and maintain order across every generation of the voyage. 20,000 people are not a crew, they are a small city. and small cities on Earth with all the advantages of open air, natural ecosystems, external trade relationships, and the psychological grounding of knowing the world extends far beyond the city limits, still experience crime, political instability, resource disputes, and social fragmentation as a matter of routine. A generation ship carrying 20,000 people must govern that population under conditions of absolute material constraint and permanent, inescapable confinement. No political system in human history has been designed to accomplish this. Every governance structure humanity has invented relies on at least one external pressure valve. Democracies survive partly because dissatisfied citizens can vote, organize opposition, emigrate, or form competing political movements. Monarchies draw legitimacy from cultural and religious traditions reinforced by relationships with neighboring powers. Even authoritarian systems maintain stability, partly through the implicit possibility that sufficiently organized resistance might succeed, a possibility that depends on the regime's access to resources and enforcement capacity, being finite and potentially exhaustible. Aboard a generation ship, the dynamics of governance become pathological in ways that have no terrestrial parallel. If the system is democratic, what prevents a majority from voting to abandon the mission entirely to turn the ship around, or to simply stop accelerating toward the destination and live aboard indefinitely? The founding generation selected the destination. The seventh generation inherited it without consent. What moral authority does a decision made centuries ago carry over people who were born into its consequences and had no voice in its formation? On Earth, democratic systems allow future generations to revise the commitments of their predecessors because the world remains open and the mechanisms for revision remain accessible. A generation ship whose mission can be revised by its inhabitants may see that mission dissolved by people who feel no living connection to a destination chosen by ancestors they know only through institutional memory. A generation ship whose mission cannot be revised by its inhabitants is a dictatorship of the dead imposed upon the living. If the system is authoritarian, the standard pathologies of concentrated power are amplified without limit by the conditions of confinement. Power corrupts. In a sealed environment with no external oversight, no possibility of regime change through outside pressure, and no avenue of escape for the oppressed, power corrupts absolutely and permanently. A tyrannical governing council aboard a generation ship cannot be checked by external forces because there are no external forces. Oppressed populations on Earth can flee across borders, appeal to international institutions, or receive material support from outside parties. A generation ship population has no borders to cross, no international body to petition, and no outside world that even knows they exist. Religious or ideological governance has been proposed by several generation ship theorists as a more stable alternative grounding authority in transcendent principles rather than individual leaders, and providing the shared framework of meaning that secular governance may struggle to sustain across centuries. History offers partial encouragement. The Benedictine monastic tradition, founded in the 6th century, persists today. Certain Jewish communities maintained cultural and religious identity across millennia of diaspora and persecution. But every durable religious institution survived within a larger civilization that provided economic context, cultural reinforcement, and a continuous supply of voluntary new members drawn from the surrounding world. A generation ship religious community would exist in total isolation, with no broader civilization to provide context and no external population to draw converts from. Sealed religious communities in history have consistently followed one of three trajectories: intellectual stagnation, doctrinal rigidity, or internal schism. These are not exceptional outcomes. They are the documented norm for every isolated religious community in the historical record. Cultural transmission compounds the governance challenge in ways that operate beneath the level of political structure. The skills, knowledge, and institutional memory required to maintain the ship must pass from each generation to the next without meaningful degradation. This encompasses not only technical knowledge about reactor maintenance and atmospheric chemistry, but the entire framework of social norms, historical understanding, and mission context that gives the voyage its meaning and its structure. On Earth, cultural transmission operates through a vast, redundant ecosystem of institutions. Schools, universities, libraries, museums, professional associations, apprenticeship networks, media organizations, and informal community practices all contribute to preserving and transmitting knowledge across generations. These institutions overlap and reinforce each other. If one fails, others compensate. If a university closes, its knowledge persists in the memories of its graduates, in competing institutions, in published literature, and in the broader intellectual culture that surrounds it. A generation ship must replicate these transmission functions with a fraction of the institutional infrastructure and no external redundancy of any kind. The fragility of knowledge transmission in isolated communities has been documented with uncomfortable clarity. The Aboriginal Tasmanians, separated from the Australian mainland by rising sea levels approximately 10,000 years ago, gradually lost several technologies their ancestors had possessed, including the manufacture of bone tools and, by some analyses, the production of cold weather clothing. This regression did not occur because Tasmanian people were less intelligent or less capable than their mainland counterparts. It occurred because their small, isolated population could not maintain the full breadth of specialized knowledge that a larger, interconnected population preserves through distributed expertise and overlapping transmission pathways. When the specialists died without fully trained successors, the knowledge died with them. The community continued. The knowledge did not. A generation ship faces an equivalent vulnerability at every level of its technical operation. Specialized knowledge is maintained by specialists. If the ship's nuclear engineering cohort in a given generation numbers 5 or 10 people, a reasonable figure for a population of 20,000 with many competing labor demands and a disease outbreak or industrial accident kills several of them before they have fully trained their replacements, that knowledge is diminished or lost. The reactor continues operating on its existing maintenance schedule, managed by whoever remains. But when a novel failure mode emerges 2 generations later, the crew may lack the institutional depth to diagnose and address it, because the chain of expert transmission was broken decades earlier in a crisis that seemed contained at the time. Language itself will drift across the centuries. Linguists have established that all living languages change continuously through phonological shifts, grammatical evolution, vocabulary, transformation, and semantic drift. The rate of change accelerates in isolated populations because there are fewer speakers to enforce conservative linguistic norms and no contact with external communities to stabilize shared usage. Research associated with generation ship studies has estimated that a sealed shipboard population would develop a distinct dialect within a few generations and a potentially mutually unintelligible language within 10 to 20 generations. This linguistic drift carries consequences far beyond cultural curiosity. Technical documentation composed by the founding generation operating manuals, engineering specifications, safety procedures, maintenance protocols, scientific records would become progressively more difficult for later generations to read without dedicated translation effort. The literature that preserves critical operational knowledge would gradually transform into archaic text, requiring interpretation rather than direct comprehension. Unless the ship maintains a rigorous, continuously enforced program of linguistic standardization across every generation of the voyage, the documents that contain the instructions for keeping the population alive would slowly become inaccessible to the very people whose survival depends on them. Children complicate the generation ship in ways that no other category of inhabitant does, because children must be formed entirely by the environment aboard. An adult who boarded at launch carries memories of Earth, of open landscapes, of weather, of cultural variety, of a world with genuine horizons extending beyond any structure. A child born in the 4th generation carries none of this. Their entire cognitive and emotional development occurs within the ship's interior. Their understanding of normal is the ship. Their concept of the world is bounded by the hull. Their social universe consists of the same few thousand faces they have known since before they could speak. Developmental psychology has established that environmental richness profoundly shapes children's cognitive and emotional growth. Exposure to natural environments improves sustained attention, reduces physiological stress markers, and supports the development of spatial reasoning and creative thinking. Variety in social interactions builds the theory of mind, the capacity to recognize that other people hold different perspectives and beliefs from one's own. Exposure to diverse cultural practices cultivates cognitive flexibility and adaptive problem-solving. A generation ship can attempt to approximate some of these inputs through carefully designed green spaces, varied architectural environments within the habitat sections, and structured social programming. But the approximation is bounded by the ship's finite interior volume and its fixed population. A child growing up aboard will never see a horizon. The longest unobstructed sightline inside, even a very large rotating habitat, might extend a few hundred meters before curving back toward the structure. They will never experience weather that was not programmed. They will never encounter an animal that was not deliberately included in the ship's managed ecosystem. They will never meet a stranger in the deepest sense of that word, because every person aboard is part of the same small community and has been known at least by name and role since before the child was born. The educational challenge is even more acute than the developmental one. The ship requires each generation to produce a specific distribution of skilled professionals, life support engineers, agricultural specialists, nuclear technicians, physicians, fabrication machinists, water systems operators, computer administrators, teachers, and governance personnel. The population is far too small to support a free labor market where individuals choose careers based solely on interest and aptitude. The ship needs specific roles filled in specific numbers, and the educational system must channel children toward those roles whether or not the children find them compelling. On Earth, educational systems can tolerate substantial inefficiency because the economy is large and diverse enough to absorb people who change careers, pursue unconventional paths, or fail to develop immediately marketable skills. A generation ship cannot afford this flexibility. If too few children in a given generation elect to study nuclear engineering, the reactor maintenance team shrinks in the generation that follows. If too many pursue artistic or humanistic interests at the expense of technical training, the ship's operational capacity degrades incrementally but irreversibly. Education aboard a generation ship is not a pathway to personal development. It is a resource allocation mechanism, and children are the resource being allocated. This creates a tension between individual autonomy and collective survival that no educational philosophy has satisfactorily resolved. Allow children to follow their genuine interests and risk critical skill shortages that emerge a generation later. Or assign educational tracks based on aptitude assessment and ship requirements, producing a technically competent workforce at the cost of personal freedom and intrinsic motivation, which in turn degrades the social cohesion the ship depends on for long-term stability. The first approach risks the operational capacity of the vessel. The second risks producing a population of resentful, alienated workers performing duties they did not choose in a world they cannot leave, a psychological condition with documented and severe social consequences. Teaching children about the destination presents its own pedagogical difficulty that compounds with every passing generation. How do you convey the significance of a planet that no living person has visited, that exists only as archived data compiled by people who died before the children's grandparents were born? How do you motivate a 12-year-old to care about a world they will never reach, when the world they actually inhabit is the only reality they have ever known? How do you prevent the destination from becoming so abstract, so remote from any lived experience, that it loses all motivational force entirely? Terrestrial education draws constantly on experiential reference points that feel real because they connect to a world the student can touch, travel to, or at minimum observe through a window. Aboard a generation ship, every reference to the universe outside the hull is mediated through recordings, simulations, and inherited narrative. The educational system must somehow transmit not merely information but felt significance about realities that no living person aboard has directly experienced. If it fails, If the destination becomes merely a word in a curriculum rather than a living aspiration, then the motivational foundation of the entire mission erodes at its deepest level. The adults who lose faith in the mission were once children who were never given a reason to believe in it that felt genuinely real. The mission does not die in a dramatic moment of collective rejection. It dies quietly, in a classroom, when a child asks why they should care about a star they will never see, and the teacher standing before them does not have an answer that resonates. Mission drift is the term that captures what happens when an institution's original purpose gradually dilutes, shifts, or disappears entirely as the people carrying out that purpose are replaced by successors with different experiences, different priorities, and different values. Every long-lived institution on Earth has experienced some form of mission drift. Universities founded to train clergy now teach engineering and commerce. Military orders founded for holy war now operate hospitals and humanitarian programs. Colonial outposts established for resource extraction became independent nations with no allegiance to the founding power and no memory of the original mandate that created them. On Earth, these transformations are not failures. They represent healthy institutional adaptation to changing circumstances. The institution survives by becoming something different from what it began as. The original mission dissolves, but the people endure, and the people find new purposes adequate to sustain them. Aboard a generation ship, mission drift is catastrophic, because the mission is not incidental to the ship's existence. The mission is the reason the ship exists. If the 8th generation no longer understands, values, or prioritizes reaching the destination star, the entire rationale for the voyage dissolves. The ship does not become something else. It becomes nothing, a sealed habitat drifting through interstellar space with no purpose beyond its own perpetuation. And perpetuation without purpose generates its own form of civilizational crisis, because human beings do not sustain themselves on calories and oxygen alone. They require meaning. They require narratives that explain suffering and justify sacrifice. The founding generation possesses this narrative in its most potent form. They are pioneers. They chose this. They believe in the destination with the conviction of people who stood on Earth and looked upward and decided that humanity's future lay elsewhere. They can endure the hardship because they understand why the hardship is necessary. Their suffering has a context that feels real because they constructed it themselves. Their children inherit a diluted version of the same story. They were raised on the mythology of the mission. They heard the accounts of departure. They were taught the significance of the destination from the time they could first understand language. But they never stood on Earth. They never felt sunlight that was not produced by an artificial source. They never breathed atmosphere that had not been processed through recycling systems. The destination is an abstraction transmitted through education rather than a place felt through experience. Their commitment to the mission is second-hand, inherited, doctrinal in nature rather than experiential. By the 5th or 6th generation, the founding narrative has become mythology in the precise anthropological sense, a foundational story that explains the community's existence and provides its central organizing purpose, but which is received as tradition rather than lived memory. Some members of the community will passionately embrace this mythology. Others will regard it as a cultural inheritance to be respected but not personally felt. Still, others will actively contest it, arguing that the ship is their home, that the destination is an abstraction imposed by the long dead, and that the mission's requirements are an unreasonable burden on people who never agreed to bear it. This is not speculative psychology. It is the documented behavior of every long-duration isolated community in the historical record. The Polynesian voyaging cultures that settled the Pacific Islands across thousands of years of extraordinary navigation maintained their wayfinding knowledge only as long as active voyaging continued to be practiced. As island populations became self-sustaining and the immediate motivation for further exploration diminished, navigation knowledge was no longer transmitted through practice, but through ceremony. Within a few generations, it existed as ritual rather than skill. European explorers eventually encountered island communities that preserved ancient canoe designs, in their ceremonial traditions, but had no living practitioners capable of building or navigating them. The knowledge had not been forgotten in a sudden catastrophic event. It had been slowly hollowed out over generations until only the ceremonial shell remained and the functional interior was gone. A generation ship faces this same trajectory across every category of specialized knowledge that is required for arrival but not for the voyage itself. The skills needed for planetary survey, atmospheric entry assessment, surface colonization, and the construction of a permanent settlement are not the skills needed to maintain the ship during transit. If the voyage lasts 15 generations, arrival skills have no practical application for the overwhelming majority of that duration. They exist only in training, curricula, and archival documentation maintained by instructors who have themselves never used these skills in any operational context, transmitted to students who cannot imagine a situation in which they would ever need them. Maintaining genuine proficiency in capabilities that will not be exercised for centuries demands a level of institutional discipline that history suggests is extraordinarily rare even in well-resourced, externally supported organizations operating under far less extreme conditions. Each generation must invest significant resources, time, energy, instructor, attention, student commitment in training for an event that will not occur in their lifetime, or their children's lifetime, or their grandchildren's lifetime. The return on this investment is invisible to every generation that makes it. Only the generation that actually arrives will ever see the payoff, and by then the investment may have stopped being made generations earlier. The psychological burden carried by individuals born into this situation deserves careful attention because it operates at a level beneath institutional dynamics and cultural drift, at the level of a single person lying awake in a room surrounded by recycled air and artificial light, trying to understand what their life means and why they are where they are. Consider a person born aboard the ship in the 7th generation. This individual has never seen a planet, has never seen any natural landscape of any kind, has never experienced precipitation or wind or an unobstructed view of any distance greater than the interior dimensions of the habitat section. Their entire world is a structure roughly the volume of a small town, surrounded on every side by hull plating beyond which lies immediate death. Every person they will ever know already lives within this structure. Every experience they will ever have will occur within it. They will grow old within it. They will die within it. The hull is not a boundary of their world. The hull is their world. This person did not volunteer for this existence. They were born into it, the product of reproductive decisions made within constraints imposed by a mission designed by people who have been dead for over a century. Their autonomy is bounded in ways that no terrestrial citizen has ever experienced in peacetime. They cannot change careers freely because the ship's operational requirements determine which roles must be filled. They cannot choose their family size freely because population management protocols govern reproductive rates. They cannot opt out of the community because there is no outside to opt into. On Earth, even prisoners know that the world continues beyond their cell walls. Incarcerated people can imagine a future outside confinement. Many can work toward release. The entire psychological architecture of imprisonment, including its most severe psychological torments, depends on the existence of an outside, a world that continues in the prisoner's absence, and to which they might eventually return. This knowledge, however painful, provides a cognitive anchor. There is something beyond the walls. The walls are not everything. Generation ship inhabitants have no such anchor. The ship is not temporary confinement. It is permanent reality. There is no release date. There is no parole threshold. There is no world beyond the hull that they could reach, even if they somehow breached it. The psychological literature on long-duration confinement in isolated environments, drawn from submarine deployments, Antarctic winter overpostings, and controlled simulations such as the Mars 500 experiment conducted in Moscow between 2010 and 2011, consistently identifies a recognizable cluster of psychological responses: depression, escalating interpersonal conflict, social withdrawal, sleep disruption, cognitive dulling, and what researchers have identified as third quarter syndrome, a characteristic motivational collapse that tends to emerge roughly 3/4 of the way through any extended confinement period, when the end is conceptually visible but still functionally distant. The confined individual has endured most of the hardship but cannot yet perceive the relief as real. These studies involve confinement durations ranging from 6 months to approximately 18 months. They document significant psychological deterioration within that window, even among highly selected, extensively screened, professionally motivated volunteers. Extrapolating from 18 months of confinement to an entire lifetime of confinement, replicated across generation after generation, with no end visible to any individual who will actually live to experience it, is not merely an extrapolation of scale. It may be a qualitative transformation into a psychological condition that has no documented analog in human experience. Now, multiply these individual psychological pressures across the entire population of the ship and project them forward across centuries. A community of 10,000 to 20,000 people experiencing chronic, low-grade psychological distress, accumulating generational resentment toward an inherited mission that grows more abstract with every passing decade. Governance structures straining under the compressive weight of permanent confinement with no relief valve and no external legitimacy. Cultural memory eroding at the edges as knowledge transmission chains break and are imperfectly repaired. And all of this occurring simultaneously, continuously, inside a sealed volume where there is no escape from any of it. Not for an afternoon, not for a weekend, not for a moment of genuine solitude in a space that extends beyond human construction. This is not a crew operating a spacecraft under challenging conditions. This is a captive civilization under permanent, total strain, asked to maintain the technical discipline and social cohesion required to keep a complex machine operational for longer than most civilizations have endured under vastly more favorable circumstances. The historical record on this point is unambiguous and offers no comfort. No human civilization has ever maintained stable governance, unbroken cultural transmission, and continuous institutional purpose for the duration required by even the shortest plausible generation ship voyage without undergoing transformation, disruption, or partial collapse along the way. The Ottoman Empire persisted for more than 6 centuries, but did so through continuous territorial expansion, the absorption of conquered peoples, periodic internal reform driven by external competitive pressure, and relationships with neighboring powers that provided both resources and the constant stimulus of outside contact. The Catholic Church has operated for nearly 2,000 years, but has survived schisms, reformations, corruption crises, and doctrinal revolutions that would have been fatal in a sealed environment, with no room for institutional competition or renewal from outside. Chinese dynastic civilization maintained cultural continuity across millennia, but through a repeating cycle of collapse and reconstruction, with each dynasty replacing the last through war or revolution before being itself eventually displaced. Every long-lived civilization on Earth survived by adapting, by absorbing external influences, by recovering from catastrophic disruptions through contact with neighboring cultures, by allowing its population the fundamental freedom to leave, to dissent, to seek alternatives, to imagine and sometimes to build something different. These are not incidental features of civilizational resilience, they are its core mechanisms. Remove them, and you have not built a more stable civilization. You have built a more fragile one that looks stable because the pressures that would normally expose its fragility have been artificially suppressed rather than genuinely resolved. A generation ship suppresses these pressures absolutely. The hull is the border, and the border does not open. The mission is the purpose, and the purpose cannot be revised by those who did not choose it. The population is the gene pool, and the gene pool does not receive new members. The founding knowledge is the intellectual inheritance, and that inheritance can only be spent, never replenished. Consider what this means across the full arc of a voyage. The founding generation deposits into the ship's collective account an initial balance of social trust, shared purpose, technical knowledge, institutional legitimacy, genetic diversity, and material resources. This balance is finite at the moment of departure and can never be increased from outside. Each subsequent generation makes withdrawals from this account, drawing on social trust to resolve conflicts, consuming material resources to maintain systems, expending institutional legitimacy to enforce governance decisions, spending genetic diversity through the inevitable reproductive constraints of a small closed population. If the withdrawals are modest and the account is managed carefully, the balance can sustain many generations, but the account earns no interest. It receives no deposits from outside. Every crisis accelerates the rate of withdrawal. Every failure of knowledge transmission reduces the balance. Every generation of conflict, drift, and degradation brings the account closer to zero. The question is not whether the balance eventually reaches zero. Given sufficient time, it must. The question is whether it reaches zero before the ship reaches its destination. And the answer depends on variables that cannot be reliably predicted before departure, on the severity of crises that cannot be anticipated, on the effectiveness of responses that cannot be pre-designed, on the behavior of human beings across centuries under conditions that have never existed. These questions involve the behavior of people in circumstances without precedent. They cannot be answered by simulation, by historical analogy, or by design. They can only be answered by the voyage itself. And the voyage, once begun, cannot be stopped. This is the deepest feature of the generation ship's irreversibility. On Earth, failed experiments can be terminated, failed institutions can be dissolved, failed civilizations can collapse, and their survivors can seek new arrangements. The failure of a generation ship civilization is not a historical event that subsequent generations learn from and move beyond. It is a death sentence carried out in real time inside a sealed container crossing the interstellar void. And yet, despite every one of these burdens, the ecological fragility, the engineering recursion, the genetic constraints, the governance pathologies, the psychological erosion, the cultural drift, the irreversibility of every failure, the generation ship concept continues to appear in serious scientific literature as the most physically plausible pathway to human interstellar settlement. Because it is. Not because it is safe, not because it is likely to succeed, but because every alternative requires either physics that does not exist or technology whose fundamental feasibility has not been demonstrated. Cryogenic sleep remains speculative. Relativistic travel remains energetically impossible. Faster-than-light travel violates established physical law. If human beings are ever to reach another star in biological form, carrying their bodies and their minds and their civilization across the void, the generation ship or something functionally indistinguishable from it is what the laws of physics appear to require. The brutal implication is not that generation ships are one option among several. The brutal implication is that they may be the only option, and the only option may be one that no human civilization has ever demonstrated the capacity to execute successfully. Everything examined so far has followed a single direction, a narrowing. The ecological margins tighten with each generation. The engineering tolerances shrink as components age beyond their designed parameters. The social fabric thins under the accumulated weight of confinement and inherited obligation. The psychological reserves deplete in ways that no amount of careful pre-launch screening can prevent across centuries of transmission through people who were never screened at all. And what remains after every system has been calculated and every structure tested against the full weight of human history is a question so fundamental that it precedes every technical specification and survives every engineering solution. Can a human civilization be built to order and expected not to fail? Not a machine, not an ecosystem, not a government, a civilization. The full architecture of human collective existence, language, memory, purpose, trust, knowledge, cooperation, identity, meaning all of it sealed inside a container, launched into darkness, and asked to persist without meaningful interruption for longer than most of the civilizations that have ever existed on Earth, lasted under vastly more forgiving conditions. The Roman Empire is cited most often when people reach for examples of institutional longevity. It endured in its Western form for roughly 5 centuries, and in its Eastern continuation as the Byzantine Empire for nearly 15 centuries in total. But the Rome that fell in 476 bore almost no resemblance to the republic that preceded the empire, which bore limited resemblance to the early kingdom, which bore little resemblance to the modest settlement on the Tiber that tradition places in 753 BCE. Roman civilization persisted not by remaining stable, but by transforming continuously and profoundly. It absorbed new peoples, adopted new religions, reformed its governance structures repeatedly, expanded and contracted its territorial reach, survived civil wars and epidemic disease and military invasion, and reinvented itself across the centuries into something its founders would not have recognized. Each transformation was made possible by contact with the broader world, by the influx of new populations, new ideas, new resources, and new pressures that forced adaptation and made renewal possible. A generation ship cannot transform in these ways. It cannot absorb new peoples because no new peoples exist within reach. It cannot adopt new resources because the hull contains everything it will ever have. It cannot expand its boundaries because the hull is the boundary, and the hull does not grow. The only adaptive mechanism available to it is internal reorganization, and internal reorganization in a closed system is zero-sum. Every change that benefits one faction disadvantages another. The political, social, and material flexibility that allowed terrestrial civilizations to survive across centuries is precisely what a sealed interstellar vessel structurally cannot possess. This is not a limitation that better engineering can eventually overcome. It is not a problem that more sophisticated social planning can solve. It is a structural feature of the concept itself. A generation ship is defined by its closure. Sealed materially, sealed socially, sealed informationally, nothing enters and nothing leaves. The system must generate all of its stability from internal reserves. And internal reserves are finite by definition. Every conflict resolved consumes social capital that cannot be replenished from outside. Every material crisis overcome depletes physical resources that cannot be restocked. Every generation that maintains cohesion does so by drawing on cultural and institutional deposits laid down by predecessors, deposits that are diminished by the very act of drawing on them and that cannot be renewed by any mechanism available within the hull. Think of it as an inheritance that can only be spent and never earned. The founding generation deposits into the ship's collective account an initial balance, social trust, shared purpose, technical knowledge, institutional legitimacy, genetic diversity, material resources. Each subsequent generation makes withdrawals. If the withdrawals are modest and crises are managed effectively, the balance sustains many generations, but the account earns nothing. It receives nothing from outside. Every crisis accelerates the rate of withdrawal. Every failure of cultural transmission reduces the balance by an amount that may not become visible until several generations later, when the knowledge that was imperfectly passed forward proves inadequate to a challenge the previous generation could have addressed with ease. The question is not whether the balance eventually reaches zero. Given sufficient time and the compounding of every category of burden described throughout this examination, it must. The question is whether it reaches zero before the ship reaches its destination. And that question cannot be answered before departure, because it depends on the behavior of people across centuries under conditions that have never existed, behavior that cannot be simulated, predicted, or designed around with any reliable confidence. The failure modes that matter most are not the dramatic ones, not the hull breach, not the reactor explosion, not the pathogen that kills half the population in a single generation. These catastrophic scenarios are the ones that generation ship engineers spend the most time designing against, and with sufficient redundancy and careful planning, many of them can be made unlikely. The failure modes that are most probable are the quiet ones, the ones that accumulate invisibly across generations, the ones that look like stability until suddenly they do not. A governing council that gradually concentrates power across 3 generations until it can no longer be meaningfully constrained. A knowledge transmission chain that loses one critical specialist in each of 5 consecutive generations until the expertise no longer exists in any living person aboard. A crop variety that suffers from accumulated soil chemistry drift until its yields fall below nutritional adequacy in a way that took 80 years to develop and cannot be reversed in less than 20 more. A population whose psychological baseline shifts across generations toward a form of resigned passivity that looks like social stability but represents the exhaustion of the motivational reserves that active mission maintenance requires. None of these failures announces itself. None of them produces a moment of dramatic crisis that the crew can respond to with heroic collective effort. They are processes, not events. They develop across timescales longer than human careers, longer than human lives, longer than the institutional memory of the generation experiencing their consequences. By the time any of them becomes visible enough to be recognized as a crisis, the capacity to respond to them may already be compromised by the very processes that produced the crisis in the first place. Science fiction has explored this scenario with persistent imaginative attention because writers recognized its plausibility long before engineers were prepared to confront its implications directly. Robert Heinlein's Orphans of the Sky, published in its final form in 1963 but originating in novellas from 1941, depicted a generation ship whose inhabitants had forgotten entirely that they were aboard a vessel believing the ship to be the whole of existence, with no conception of a universe beyond its walls. Brian Aldiss's 1958 novel Non-Stop portrayed a similar civilizational amnesia, with the ship's later generations living as tribal communities inside a vessel they no longer comprehended as a machine, navigating corridors overgrown with vegetation and interpreting the ship's systems as features of a natural environment they had never understood as artificial. These are not merely imaginative exercises. They are extrapolations of documented human behavior in isolated communities projected across the timescales that generation ship voyages would require. The ancestral Puebloan civilization of the American Southwest built elaborate multi-story cliff dwellings and sustained a complex agricultural society across centuries before prolonged drought, resource depletion, and social fragmentation drove total abandonment of their most developed settlements by the late 13th century. The Rapa Nui civilization on Easter Island deforested their entire island ecosystem, collapsed the agricultural base that had sustained them, and descended into conflict and severe population decline, a civilizational unraveling driven not by external catastrophe, but by the internal logic of a closed system, consuming its own resource base faster than it could regenerate. The Norse colony in Greenland persisted for roughly 4.5 centuries before failing entirely, its last inhabitants dying in a landscape they could no longer sustain themselves within, having maintained cultural practices adapted to a different environment, rather than adapting to the one they actually inhabited. Each of these cases involved populations living on a planet, breathing unprocessed atmosphere, drinking water from natural sources, standing under an open sky with genuine horizons extending in every direction. Each had access to sunlight, to biological ecosystems that provided buffers against local failures, and to the deep psychological grounding that comes from inhabiting a world that was not built by human hands and does not depend on human maintenance to continue existing. And each nonetheless experienced severe cultural regression, catastrophic knowledge loss, or civilizational collapse. A generation ship offers none of these environmental supports. It demands that a human community maintain perfect institutional continuity in the most artificial, constrained, and psychologically demanding environment ever proposed for long-term human habitation. The radiation keeps falling throughout all of this. That fact deserves emphasis because it illustrates with particular clarity how physical and human burdens interact and amplify each other across generational time. Galactic cosmic ray exposure does not pause during a political crisis. DNA damage does not slow because the medical team lost several specialists to an accident. Cancer rates do not stabilize because the population is simultaneously managing a food production shortfall and a governance dispute. The radiation is constant, indifferent, cumulative. Each generation is biologically slightly more burdened than the one before. Each generation faces a marginally higher prevalence of chronic illness, a marginally smaller pool of fully healthy working adults, a marginally greater demand on medical resources that are themselves aging and being maintained by a workforce that is itself experiencing the biological consequences of cumulative radiation exposure. Over 5 or 10 generations, this biological erosion remains within manageable bounds for a well-designed system with adequate initial resources. Over 20 or 30 generations, it becomes a systemic drag on the population's capacity to maintain everything else: more people requiring care, more labor hours devoted to managing illness, fewer skilled workers available for critical technical maintenance, a genetic burden that reduces the effective functional population below the number physically present aboard the vessel. A ship that departed with 20,000 people might, in its 15th generation, have 18,000 people alive, but of those, perhaps 14,000 healthy enough to perform sustained physical and cognitive work. And of those 14,000, only a fraction will hold the specialized knowledge required for the most critical maintenance tasks. The ship is not understaffed by the numbers on the population registry. It is understaffed by the intersection of health, training, and specialized competence that determines how many people can actually perform each necessary function at any given moment. This is the convergence point where every category of burden arrives simultaneously. The engineering systems degrade, the ecological margins narrow, the genetic health of the population erodes, the social structures strain under accumulated pressure. The cultural memory fades at its edges. The psychological resilience of the population diminishes across generations of inherited confinement, and each of these processes accelerates every other one. Sicker people maintain systems less effectively. Poorly maintained systems produce environmental conditions that worsen health outcomes. Worsening health intensifies social conflict over resource allocation and governance decisions. Social conflict disrupts knowledge transmission and training pipelines. Disrupted training leads to less effective maintenance of every physical system aboard. The spiral does not tighten at a constant rate. It tightens at an accelerating rate, and the resources available to arrest it diminish in direct proportion to the severity of the problem they are being asked to address. No single one of these burdens is necessarily fatal in isolation. A well-designed ship might survive a period of severe social instability without losing critical technical functions. A robust and genetically diverse population might absorb an elevated cancer rate without the medical system collapsing. A skilled engineering team might manage a complex cascade of mechanical failures and restore operational stability. But the generation ship does not face any one of these burdens in isolation. It faces all of them simultaneously, continuously, and cumulatively across a duration that exceeds every comparable human achievement, using a fixed and declining inventory of resources to address problems whose severity increases with time. The question is not whether any individual challenge can be overcome. The question is whether all of them can be overcome at once by the same population, using the same finite reserves across centuries, without a single generation of the kind of failure that every human civilization has eventually experienced. And here is the thought that should stay with you long after this ends. The generation ship concept is not wild speculation. It is not the province of science fiction enthusiasts unwilling to accept physical reality. It is the most physically plausible method of interstellar human migration that the known laws of physics permit. Cryogenic sleep has not been demonstrated. Relativistic travel demands energy that exists nowhere in human engineering. Faster-than-light travel violates the foundations of established physical law. If human beings are ever to reach another star, carrying their bodies, their minds, their memories, their civilization across the interstellar void, the generation ship, or something functionally indistinguishable from it, is what the universe appears to require. This is not one option among many. This may be the only option, and the only option may be one that humanity has never demonstrated the capacity to execute. Not because we cannot build the ship. We probably can. Given sufficient resources, sufficient political will, and continued technological development across the coming centuries, the material science is challenging, but not implausible. The propulsion requirements are enormous, but not beyond what nuclear or fusion technology might eventually provide. The ecological engineering is deeply daunting, but grounded in principles that are well understood, even where execution at scale remains undemonstrated. The physical vessel, the hull, the reactors, the atmospheric systems, the rotating habitat, the agricultural infrastructure can probably be built. The civilization inside it probably cannot be guaranteed to survive. This is the inversion that most people never see coming. The brutal reality of generation ships is not a catalogue of engineering problems that future technology will eventually solve. It is the recognition that the hardest component of interstellar travel has nothing to do with propulsion systems or shielding materials or closed-loop ecological chemistry. The hardest component is the people. The hardest component is asking a human society to do something no human society has ever done to survive: sealed, isolated, confined, and purposeful for longer than any nation or empire or religious tradition has ever persisted, without transformation, without interruption, and without collapse. The ship is not the challenge. The civilization is the challenge. And civilization, it turns out, is the most fragile machine our species has ever attempted to construct. More fragile than the hull plates that must hold against the vacuum for centuries. More fragile than the reactor vessels that must contain their nuclear cores for generations. More fragile than the atmospheric recyclers and the water purifiers and the carefully managed agricultural systems and the genetically curated population and every other system aboard, because it is the one system that cannot be repaired with fabricated components, cannot be restored from archived specifications, and cannot be restarted once it has stopped functioning. A hull breach can be welded. A reactor malfunction can be diagnosed and addressed by engineers with the right knowledge and materials. An atmospheric imbalance can be detected and corrected by people who understand what the sensors are telling them. But a civilization that has lost its purpose, or fractured beyond the capacity for collective action, or forgotten the knowledge required to maintain the systems keeping it alive, that civilization cannot be repaired from the inside by the people who are already lost within it. The first generation ship, if it is ever launched, will carry more than its listed manifest of passengers and provisions. It will carry the most consequential experiment in the history of the human species. An experiment to determine whether Homo sapiens, a creature that evolved on open savannas beneath limitless skies, that built its civilizations through contact and exchange, and the constant renewal that comes from encountering the genuinely new, can sustain a functioning civilization inside a metal world smaller than a village, crossing a void wider than comprehension, for longer than recorded history has ever sustained anything. The experiment has no control group. It cannot be repeated if it fails. Its subjects did not consent, because the majority of them had not yet been born when the decision was made, and its outcome will be determined not by the tensile strength of the hull, or the efficiency of the power systems, or the yield of the crops, or the diversity of the gene pool, but by something far more fragile than any of these and far less understood: the ability of human beings to remain human, to remember who they are across the silence of generations, to maintain trust and cooperation and shared purpose inside a world with no horizons and no seasons and no sound of wind, to pass forward not merely the technical knowledge required to keep the systems running, but the felt sense of why the systems matter, why the destination is real, why the voyage is meaningful, why the sacrifice of the intermediate generations is justified by something more than the abstract aspirations of people who have been dead for a century. In a world without horizons, every generation ship proposal is, at its deepest level, a wager that human nature is robust enough to endure the most extreme and sustained isolation ever imposed on a population. A wager that social engineering can achieve across centuries what no social system has ever achieved across decades. A wager that the accumulated weight of closed ecosystems slowly degrading, machinery slowly wearing, radiation slowly accumulating, genetic health slowly eroding, cultural memory slowly fading, and psychological resilience slowly depleting, will not across the full arc of the voyage produce a failure. Cascade that transforms the arc into something the founding generation would not have recognized as the ship they launched. The honest assessment grounded in everything we know about human societies, about closed ecosystems, about material degradation and population genetics and the psychology of prolonged confinement, is that this wager carries odds that no serious analyst would describe as favorable, not impossible. Humanity has surprised itself before, in ways that appeared impossible until the moment they became real. But the margin for success is narrower than almost any generation ship advocate publicly acknowledges, and the consequences of failure are not a setback from which lessons can be drawn and applied to the next attempt. The consequences of failure are absolute and permanent and silent. The stars are not beyond reach because the distance between them is too great for any conceivable vessel to cross. The stars are beyond reach because the bridge required to cross that distance is not constructed from metal or fuel or engineering brilliance. It is constructed from human continuity, from memory and purpose, carried forward intact by people who did not choose their circumstances, through a darkness that offers nothing in return, toward a light that most of them will never live to see. The generation ship does not fail because the distance is too vast. It fails if it fails because the distance demands something of us that we have never demonstrated we can reliably sustain across the timescales involved. Not speed, not power, not ingenuity. Endurance. The endurance of a civilization that cannot afford a single century of the kind of failure that every civilization in the full span of human history has eventually experienced. The void between the stars is real and it is immense. But the void inside a sealed vessel, the void where meaning and purpose and social cohesion must be manufactured continuously from nothing but human will, with no external world to draw from and no horizon to orient by, may be the greater distance. And, crossing that interior void, keeping a human world intact and purposeful and alive across the long silence between departure and arrival, may be the single most difficult thing our species could ever attempt. The first true interstellar arc, if it is ever built, will not fail because humanity could not endure the physical journey. It will fail, if it fails, because keeping humanity intact proved harder than crossing the distance, because the ship was never the true challenge. The civilization was. And civilization, it turns out, is the most fragile thing we have ever tried to carry anywhere. More fragile than the hull, more fragile than the reactor, more fragile than the atmosphere and the water, and the carefully tended crops and the managed gene pool, more fragile than anything else aboard. Because it is the one cargo that cannot be inventoried before departure, cannot be inspected during transit, and cannot be recovered after loss. The warmth is here now, on this world, in this moment, beneath an open sky with real horizons extending in every direction, under light that travels 93 million miles from a star we did not build and do not need to maintain. It is extraordinary, it is temporary, and it is awesome.